Hello ladies and gentlemen, this is the introduction to Chapter 4. This is Chapter 4, Section 1, applying the triangle sum properties. First, since we're talking about triangles, we need to do a review of the different types of triangles. And remember that a triangle, usually denoted by this triangle symbol in the textbook, is just a three-sided, specifically polygon. Polygon, again, is a closed plane figure. It's flat with no openings. There's no curves involved. All of the sides are made up of lines. So it has these sort of qualifications for it. It can't have any overlapping sides, is the third one. So the different types of triangles, you can classify them by sides or you can classify them by angles. Classifying by sides, we have a scalene triangle where no two sides are the same. Isosceles, at least two congruent sides, so we denote that by those congruent tick marks. And three congruent sides would be equilateral, which have three sets of matching tick marks. So all three sides would be congruent. We talked about equilateral back in Chapter 1, Section 6. If we're going to classify them by angles, an acute triangle has three acute angles. A right triangle has one right angle, 90 degrees. An obtuse triangle has one obtuse angle, at least one of them is larger than 90 degrees. And equiangular, all three of the angles are going to be the same, three congruent angles. And as a reminder, an acute angle is any type of angle that is less than 90 degrees. So there's a brief review of the different types. We should already know these and be familiar with these. Brief review, if you need to pause it to write these down, or if you want to rewind the explanations, that's fine. Otherwise, we're going to move forward into some of the examples. For this one, we're given this triangle and we're asked to classify it by its sides and by its angles. So looking at the sides here, let me highlight this in a brighter color. I'm given that two sides are matching here, are congruent. So the most is that I can say it's an isosceles triangle, classifying it by sides. And if I'm classifying it by angles, all these angles, we don't know if they're equal, but they do all appear to be less than 90 degrees, so I can call this an acute triangle. If I wanted to combine these into one word, I could also just say an acute isosceles triangle if I want to combine it into one single statement, and that would be permissible. And that's classifying it by sides and by angles. A nice review, you should have done these things in middle school. We're going to add a few different things today that are more applicable to high school. So let's move on to another one. Again, we're going to classify it by its number of sides, but in the coordinate plane. So using our distance formula to find the length of each side, see if any of them are congruent. Then we'll determine if it's a right triangle. Well, a right triangle means that it has a right angle. We'll do this part first. If it has a right angle, it means the two of our sides are perpendicular. So we need to find the slope of each side and see if any of our slopes are opposite reciprocal, because they need to be perpendicular in order to, to know that there is a right angle. So to find the slope of each side, I'll count the rise over the run. So here I'm rising 1 and running 1, 2, 3, 4, 5, 6, 7. So this slope is positive 1 over 7. Now we're counting this side, I'm moving down 2 and right 1. So it's going to be negative 2 over 1. And lastly, here I'm moving up 1, 2, 3, and right 1, 2, 3, 4, 5, 6. That's going to be positive 3 over 6, which is also positive 1/2. Well, now I notice two of my slopes are opposite reciprocals. One is negative 2 over 1. One is positive 1/2. So my purple and red together, this line and this line, form a right angle because those two lines are perpendicular. So the first thing I'll say is yes, this is a right triangle. The second part takes a bit longer. That's why I did this first. We're going to classify it by sides. That means we're going to have to find the length of each side. And to find the length of each side, we'll have to use our distance formula. And I'm sure as soon as I said distance formula, some of you watching this at home or wherever you might be probably groaned. So we have to talk about what type of triangle it is with sides. So let's use our distance formula to find the length of this short side first. So distance formula, distance equals the square root of y2 minus y1 squared plus x2 minus x1 squared. Looking at my x's and my y's, I'll say this is x1, y1, x2, and y2. And I'll plug those in. So my y2 minus y1 is 0 minus 2. x2 minus x1 is 0 minus negative 1. Now it's just simplifying and using my order of operations. 0 minus 2 is negative 2, and 0 minus negative 1 is the same as 0 plus 1. After parentheses are finished, I'll use my exponents. Negative 2 to the second power is positive 4, because I leave this in parentheses. And then 1 squared is simply 1, so this is the square root of 5. I'm going to leave it as the square root of 5 to be an exact answer. So this side here is the square root of 5. We also probably could have skipped that because obviously this side isn't congruent to the other two sides. So we probably could have skipped this step in this particular problem, but for it being our first problem, I'm going to do all three sides with our distance formula. So let's do another side with our distance formula. Let's find the length of this side here. So I have to relabel what's x1, y1, what's x2 and y2. I'll let this be x1, y1, x2 and y2. So plugging those in, this will be 3 minus 0 squared and 6 minus 0 squared. To simplify my parentheses, 3 minus 0 is 3, 6 minus 0 is 6. I'll use my exponents next, so 9 plus 36, and that should give me the square root of 45. So far, it's not going to be equilateral. It may be scalene or isosceles, so we shall see. We have to find our third side now. That means this side up top, and we'll have to pick a different x1, y1, and a different x2, y2. So I'll say that the one on the left is x1, y1, the one on the right is x2, y2, so let's do this third time. Y2 minus y1 is 3 minus 2 squared, plus x2 minus x1, 6 minus negative 1 squared. And this is really the same as 6 plus 1 because when you subtract a negative, it's the same as adding a positive. 3 minus 2 is 1 to the second, and 6 plus 1 is 7 to the second. If I simplify this, it's 1 plus 49, which is the square root of 50. I should probably do that in blue, actually. So none of these sides are the same length. Square root of 5, square root of 45, and square root of 50. So this is going to be a scalene triangle because none of the three sides are congruent. Distance formula takes a bit of time. Same concept, just plugging in that algebra property here as well. For some vocab, just so you're aware when we do specific theorems, that interior angles are whatever angles are inside our triangle. And if we're talking about exterior angles, those are formed by extending the sides of our triangles. So they keep on going like they're lines instead of line segments. And if we were to extend these lines together, our exterior angles are on the outside. So they're somewhere formed out here. Those are our exterior angles. We do not include the ones that are vertical outside here. It's just the ones that form linear pairs. So it's not going to be any of the vertical angles, only if they form a linear pair with the side of the triangle. So in that case, it would just be the orange angles. So those are our exterior angles. The triangle sum theorem, you all should know this, that the sum of the measures of the interior angles, so the angles that are inside, if you add these together, it should equal 180. That's the triangle sum theorem. For a proof of that, you can look at this here. If you would like to take a look at a proof, if you're curious of how this was proven by Euclid. Otherwise, you can go ahead and use this theorem as fact because it has been proven. So that's our triangle sum theorem. A second theorem that was proven is the exterior angles theorem, which says the measure of an exterior angle of a triangle is equal to the sum of the measures of the two non-adjacent interior angles. What all of that is saying is that if I were wanting to find angle 1 out here, I would add the two interior angles that are farther away from it, that are not adjacent. So not this one here, but the two that are further away from it, the non-adjacent angles. So angle 1 is equal to measure A plus the measure of angle B. That's the exterior angles theorem. And there's a proof of that on example 50 on page 223 if you want to take a look at that for some proof. That's our exterior angles theorem. And we'll use those in some examples in order to solidify how we're understanding that. To find the measure of JKM, so JKM, which is this exterior angle here, we need to use our exterior angle theorem, which says that if you find the exterior angle, it's equal to adding the two remote interiors or non-adjacent interiors together. So 2x minus 5 should equal adding x and 70. You're adding the two angles that are across from it inside your triangle. So here to solve for x, I'll subtract x from both sides, so they're all on the left. And these cancel, so I have 1x minus 5 equals 70. Then I'll add 5 to both sides. These cancel, and x is 75. If you would like to check this, if this angle should be 75, that means this linear pair angle inside of here. Hold on a second, is that correct? 2x minus 5 equals x plus 70, subtract x plus 5. Doesn't look like it's trying to, oh, that's what x is. Ah, so you see I just caught my own mistake. We're not asked to solve for x, we're asked to solve for the angle. The angle is 2x minus 5. So if I plug x back in, which is 75, this is 2 times 75 minus 5, which is 145 degrees. So this exterior angle, my mistake, is 145 degrees. Now we're finished with the problem. You see how easy it is to stop at x and not read the problem carefully. Now, if we wanted to check our answer, this angle inside here, which is a linear pair, should be 35 degrees, because they should add to 180, so that's 35. My x was 75. So if I add 75, 70, and 35, my three interior angles, it should equal 180. If I add those, indeed, I do get 180, so it checks out. It's a long way to check it. It's not quite as quick as some other check methods we've looked at before. Again, your final answer is 145. We solve for x using our exterior angles theorem, plugged it back in for x, so our exterior angle was 145 degrees. The last thing we're going to talk about is a corollary. A corollary is kind of similar to a theorem. It's basically something that's easily proven using a theorem. So it's still kind of a theorem in that it needs to be proven, but it's something that's very easily proven with maybe 1 or 2 steps using a theorem. The corollary to the triangle sum theorem, so it kind of piggybacks on the triangle sum theorem, it says the acute angles of a right triangle are complementary. If this is 90, then these two should add together to get 90. Because if these add to give us 90, and we add this 90, the whole thing equals 180. And there's a proof of that right here that basically goes over what I just said. It's just a nice shortcut that you can use. So if this is 90, these two should add up to equal 90 as well. So the whole thing equals 180. There's an example. We'll do an example of that. We'll also do an example of the other two before we finish today. For number 3, we're going to find the measure of angle 1 in the diagram shown. Well, to find the measure of angle 1, we can use our triangle sum theorem, but we don't know the other two angles. We only know 40. We don't know what x is. So we need to solve for x. To do that, we'll use our exterior angles theorem, which says that 5x minus 10 equals adding my 3x and 40. Subtracting 3x from both sides, 2x minus 10 equals 40. Adding 10 to both sides, 2x equals 50, so x equals 25. From here, I can go one of two ways. I can plug in 25 here to get 75, and I know that 75 plus 40 plus 1 should equal 180. Or I should say the measure of angle 1. And if you combine like terms, 75 and 40 should give me 115. And if I subtract 115 from both sides, the measure of angle 1 should be 65. That's one route I could go with it. Other route is if I plug in 25 here, 5 times 25 minus 10, which should end up giving me 115. Looks familiar. These two angles form a linear pair. So I can just do 180 minus 115 to get 65 using that linear pair. Either way, you still get the answer that the measure of angle 1 equals 65. I'm going to put that here in bold just so that we know that's the final answer. Because I know that when you're writing on a quiz or a test or in a homework assignment, it helps me out if I can know exactly what the answer is. So in this case, the measure of angle 1 is 65 degrees. I'm going to erase this, so if you need to pause this to finish writing it, go ahead. For number 4, find the measure of each interior angle of triangle ABC, where the measure of angle A is x, B is 2x, and C is 3x. Well, first thing I might want to do here is draw a picture. So let me make some space. If you're not a picture person, maybe you don't have to, but a lot of students are visual. So I have a triangle where one angle is x, I'll call that A, one is 2x, I'll say that's B, the other one's 3x, I'll say that's C. If I add all three of those together, it should equal 180 using my triangle sum theorem. So x plus 2x plus 3x equals 180. If I combine these like terms, I have 6x equals 180. So x here is going to be 30. But I'm asked to find each angle, not x. So this angle, since it's just x, is 30. This angle is 2 times 30, or 60. And this is 3 times 30, or 90. And you can check if you add all three of those together, the 90, 60, 30, you do get 180. The correct answer is that x is 30, and those are the three angles that we were looking for. Last example for today. Oops, I gave way too much there. Let's go back. I don't want to give away the answer too quickly. I'll give it away and I'll just cover it back up. So shield your eyes. You saw nothing. All right. Find the measure of the acute angles of the right triangle in the diagram shown. Well, since it's a right triangle, using the corollary, we know that these should add to give us 90. You could say that all three add to give you 180, but it's unnecessary because if we add all three of them to get 180, we'll end up using this 90 and getting the same answer. This is a nice shortcut, so these should add to give us 90. So 2x plus x minus 6, nice shortcut, equals 90. Combining like terms, 3x minus 6 equals 90. I'll add 6 to both sides, so 3x equals 96. That means that x should equal 32. I'm not asked to find x, I'm asked to find the measure of each angle. So here, 32 minus 6, I end up with 26 as my answer. And up here, 2 times 32 is going to be 64. And if I add 64, 26, and 90, I do end up with 180 as a good way to check it. So I would say that the first angle is 64, my second angle is 26. This concludes lesson 4.1. Feel free to pause and rewind and check out what you need to. Ask any questions you need to in class, before class, or after class.